Now we're going to take a look at an example of actually using the Nernst equation to predict how potential of a cell can change. So we have this idea that, your cell, the potential of your cell, the flow of electrons, is based around this chemical reaction occurring. And we know that that chemical reaction we're not at equilibrium, but the reaction will progress until we reach equilibrium. And that would correspond to decreasing the amount of reactant, increasing the amount of product, and the relative ratio of those would be captured by our Q term. So basically the reaction quotient, how will this change as the cell runs? And we know it's always going to increase. And so that's going to affect how the kind of potential of the cell will change as it actually starts to run. As electrons flow, how does the kind of push for more electrons to flow, how does that vary? So let's take a look. What is the potential of this cell, the same zinc copper cell? What is the potential of this cell after 90% of the copper 2+ ions have consumed? I got the cell notation right here. Let's take a look.
We want the potential of the cell after 90% of the copper ions have been consumed. And so when we say potential of the cell, our kind of equation for that, or variable for that, would be E cell. You'll note it's missing that knot or kind of circle at the top, the degree symbol. That's what we've always calculated before, which comes from things at standard conditions. That's the tabulated information we can use, but it only applies to standard conditions. So if all of your concentrations are 1 molar. So most realistic cells are not at 1 molar. Anytime a cell has reacted some, you're no longer going to be at 1 molar concentrations. So you're going to need to account for this E cell. And whenever we want that, we need to use the Nernst equation. So whenever we want some sort of realistic cell, a cell that's already reacted some, that's always an indication that we need to use our Nernst equation. So E cell, you'll note, is equal to E cell naught minus RT over NF ln Q. So we want this thing. We want E cell. And so we want to think about, do we have all the other variables? So first off, R and F are constants. So we've talked about that you have an alternate form to the Nernst equation that where those values are just plugged in. T is not given here, but we can assume that it's room temperature, which means it's 25 degrees Celsius, which would be 298 K. So E cell naught, N, and Q are going to be basically the kind of specifics for the particular cell you're looking at. That's kind of the variability comes in when you're dealing with the Nernst equation, when you're defining your particular cell. So E cell naught and N are based on the half reactions. And Q would be based, that's the actual reaction quotient. So this reaction right here, this cell, zinc and copper, this is the one we looked at in the previous example of coming up with the reaction quotient. So we know our equation for the reaction quotient is going to be the zinc ion concentration divided by the copper ion concentration. So we're going to need to get those concentrations based on the overall chemical reaction and that sort of analysis, or that sort of insight. And so we're going to start by looking at our half reactions. And so we've seen, we can kind of look at our cell notation. And we've seen that this would be, we have the anode is zinc solid becoming Zn2 plus aqueous plus the 2 electrons. And then the cathode is 2 electrons plus the copper 2 plus becoming copper solid. And so one of the things we can see right here is I have electrons coming out, 2 electrons going in. So that leads to N equals 2. So that comes from balancing. The cell has already been kind of converted. The other thing that affects is determining E cell naught. Okay. And so we know that we can look at this. This is the reduction side. This is the oxidation half reaction. And so normally, we would kind of look at, if we were just told what half reactions were, we could look up their reduction potentials, figure out which one kind of wins or sticks with the reduction direction. But that's already been decided for us. And we can see that the copper is going to stay in the reduction direction minus the reduction of potential of zinc, because we know that one gets swapped, which has already happened. And so when we go to look up their values, we can see it's consistent that the copper line is above the zinc. So that's why the copper is positive, stays reduction, because its potential is more positive than the zinc. We plug those in, it's 0.34 volts for the copper, minus negative 0.76 volts for the zinc. We get 1.10 volts. So under standard conditions, when you're at the 1 molar, your potential is 1.10 volts. But that's only under standard conditions. Whenever you're kind of working through one of these processes, whenever you're working through the Nernst equation, one of the things, this cell potential better be positive. Your standard cell potential better be positive because that's the actual spontaneous direction. And if not getting that positive, then that means you have something wrong about your cell. Generally, it's what you're considering your anode and cathode. But this number that you're calculating out here for a spontaneous cell that is just running, that should never be negative. There should always be a positive value. So again, this E cell not, when it has that symbol, that's where we can use our reduction potentials. We can use that reference information to figure out what that value is. So we've got E cell not and N, just from kind of the chemistry that's there. Then Q, that's going to be dependent on how much of the actual reaction has occurred, what's going on in that context. So let's take a look at the actual reaction. We have our equation is Zn solid, copper 2, Zn2 plus copper solid. And what we want is the concentrations of these two things at some point in the reaction, after 90% of the copper ion has been consumed. So we're going to think about, well, where do we start? We were told that it's 1 molar concentrations. We start under standard conditions. So we can think about this as kind of like a ice table type setup, where we have our initial. We need to figure out the change. In this case, 90% of the copper ions have been consumed. So that means 90% of this is gone. So 90% of the 1 molar would mean that we would lose 0.9 mole. So the concentration that's left would be 0.1. There's 10% left after 90% reacts. So that reaction of reactants of the copper has to lead to the production of products. We know that this concentration is going to increase. So our question would be, how much does it increase by? And that's going to be based on stoichiometry. This reaction is going to completion. We don't need to worry about, this isn't an actual ice table. We don't need to worry about equilibrium. And so what we could say is, we have this 0.9 molar of the copper 2 plus that's reacting. We know that that is 0.9 moles of copper 2 plus per 1 liter of solution. And then based on our reaction coefficients, for every 1 mole of copper 2 plus that reacts, we would get exactly 1 mole of zinc 2 plus, giving us 0.9 moles of zinc 2 plus per 1 liter, which would mean we have 0.9 molar zinc cations. So there are the same number here, but that's only because the stoichiometry is 1-to-1. If your stoichiometry is not 1-to-1, you would need to make that adjustment. But what that means is this concentration goes up by 0.9 molar. So this one, the 0.9 moles reacts, goes right here. And so that means this concentration goes up. So this reflects what we know, kind of instinctively know, that the concentration of reactants goes down, concentration of products goes up as the reaction progresses, as it actually happens. So the purpose of computing these was to plug them back into Q. So Q is the concentration of zinc divided by the concentration of copper. So that's going to be 1.9 divided by 0.1, or 19. So for this particular reaction, once 90% of the initial reactants react, your Q becomes 19. So we started out under standard conditions, so we would have been at a Q equals 1. Now it's up to 19. This makes sense. We are making more product and consuming reactant. We expect Q to increase as we make more product, as more and more product is made and reactant is consumed. So our Q is up to 19. So what we're going to do then is take this number and plug it back into our Nernst equation, because we already got E cell and N. Now we can plug in on Q. So do our actual full calculation. E cell, just plug in. We calculated E cell naught 1.01 volts minus 8.314 joules per mole Kelvin times 298 K divided by N was 2 times 9.65 times 10 to the 4th coulombs per mole times the natural log of 19. We do this arithmetic, we get 1.10 volts minus this whole term comes down to 0.013 volts. Logarithm of 19 is 2.94. You could have used like the simplified version where the R and the F are plugged in. That's totally fine. The T plugged in, everything you should have evaluated still up to 0.013 volts for that part. And the units on this part are always going to be volts because it's the joule and coulomb, basically joule divided by coulombs gives you volts. Combine all of that together, do the arithmetic, we get that the cell potential is 1.06 volts. So on face, what this tells us, we started out at 1.10 volts because we started out at 1 molar concentrations, and then the potential has decreased to 1.06 volts. So it's gone down to 1.06 volts. We have seen a drop in potential. What this means, a drop in potential signifies that there's less push for electrons to flow, which really means there's less tendency for the chemistry to happen. That's because we started to make more product, right? There's less reactant left. There is less kind of driving force for the chemical reaction to occur because you have less reactant, right? There's going to be less chemistry. There's less push for electrons to flow. Still quite a bit of push, right? 1.1 dropped, it didn't drop a ton, but it has gone down. So we always expect as any reaction occurs, Q increases and the cell potential decreases. So cell potential is always going to decrease as the reaction occurs, as we consume reactant and make product, because basically we're approaching equilibrium. So there's less motivation or less chemical driving force for more and more of the reaction to occur.
So our standard conditions was, 1.10 volts, 90% of reactants, which we just looked at, drop to 1.06 volts. If you keep going, 99%, you drop to 1.03 volts, right? This is a lot of chemistry has happened. You're down to 0.01 molar zinc cations left, and still the potential is 1.03 volts. And so at the end of the day, when you're looking at a cell and you're looking at the chemistry happening, even after a huge amount of your reactants have reacted, right, 99%, your potential is still relatively unchanged. 1.03 volts is still not that different from 1.10. Now, there can be big ramifications for like batteries in terms of whether or not they work, but for what you need them. But the potential is still there. And what that really means is that basically you're still really far away from equilibrium. We would think about this as, like this, it looks like most of your zinc is gone, but at equilibrium, there should be, like no zinc atoms. Here you still have, 0.01 mole. You should, have like 10 to the negative 10th molar or something like that. But one of the things we can see is once you choose zinc and copper as your half reactions, the potential is really going to be somewhere around about 1-ish, 1 volts. Once you make that decision, once you choose what the chemical reaction is, that's really going to kind of drive the potential that you're looking at in terms of kind of the specifics. There's some variation, but not a ton. So if we kind of return to the idea of designing a cell, we said electrode material and electrolyte solutes. You don't really have much choice there. Electrolyte concentration, you do have a lot of choice. There's a lot of flexibility, and you can change the actual observed potential, but it comes down to it. Once you choose those half reactions, once you choose the chemistry, that's pretty much it. You've pretty much locked in overall what kind of range of potentials you'd be looking at. You don't have a ton of flexibility there. You can't really play with it. And you also, another important thing to think about with the Nernst equation is it kind of just reflects the fact that cells do discharge and the potentials are going to change. So it's good once you pick a chemical reaction, you are kind of guaranteed to have that you're going to have that potential for a while, somewhere around that kind of target potential. Participation 4-7, question 3. Assuming you start under standard conditions, what is the potential of the cell driven by the following chemical reaction at 298 K after 90% of the Ag plus ions have reacted? E cell naught is 1.54 volts. 3 silver plus and chromium become 3 silver and chromium 3 plus. This is the third question on participation 4-7, due Tuesday, April 7th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the links to the document where these videos are posted. Again, assuming you start under standard conditions, what is the potential of the cell driven by the following chemical reaction at 298 K after 90% of the silver plus ions have reacted? E cell naught is 1.54 volts. And we've got the chemical equation there. It's balanced, balanced chemical equation. Right, that was the third and final question on participation 4-7. You want to find all 3 of those questions, get them answered, get those answers submitted over on Blackboard by Tuesday night. Wednesday, you got the midweek 12 homework. Do it at night. Wednesday at 11 a.m. we'll do the microvoltaic cells lab. It's our final full lab activity. We'll just do kind of some other summative things after the test. Microvoltaic cells lab will be on Wednesday. Make sure you take care of the pre-lab technique notebook and all that stuff taken care of for our last time working in lab groups. If you have any questions about anything, don't hesitate to reach out. The answers to the participation will go live Tuesday night. Encourage you to take a look at them. Next week, we got test 3. If you got any questions about that, let me know. Otherwise, bye.